Okay, so hopefully by now the point that time plays a very important part in Verilog simulations is clear. Let's spend some time trying to understand what exactly is this notion of simulation time and what these delays mean. Okay. Simulation operates on the notion of discrete time steps. Time as we understand it is an analog quantity, right? I mean, yes, we think in terms of minutes and seconds, but you can go further down. You can go to milliseconds, nanoseconds. Even that's not the end, right? I mean, there is something always finer than that. But as far as Verilog simulations are concerned, at some point you have a granularity, and there is a time step that says I don't really sort of treat any smaller level of granularity than this. And what we have in general in simulations is that we have a certain time unit, and when we say hash 10, that basically means, as far as the simulation is concerned, wait for 10 time units and then proceed beyond this step. Okay. Such a notion does not exist in a C-like programming language. You never have the idea of waiting at a particular point in the program, right? There are certain programming languages. So for example, you could think of the yield operation in Python as being some vaguely similar at some level, right? It has this notion that, okay, wait for something else to happen, give up control, go out over here and then come back at a later point in time. It's similar, not exactly the same. Verilog and VHDL have an explicit notion of time associated with them, which is not generally modeled in other programming languages. Okay. Also, because of the nature of digital design, the default time unit is 1 nanosecond unless otherwise specified. Why? Because most interesting things in digital logic, at least in this day and age, happen on this time scale of nanoseconds, right? Clock periods in the order of nanoseconds, and pretty much all gate delays and so on are of a similar kind of nature. So by default, they have just chosen that 1 nanosecond is the default time scale. There is a system task, as I said, right? It's a system function which returns the current simulation time, $time. So you can actually print out what is the current simulation time at any given point in your simulation by using $time. Now, one important thing that generally has to be done in every piece of code as you go through is that you need to have a so-called timescale directive right on top. Okay, this thing which starts with a backtick, that is the backwards apostrophe symbol, right? It's called a backtick, and this backtick timescale is used in order to specify what is the time unit and the time precision. So what this means in other words is, the time unit is 1 nanosecond, which means a hash 1 basically means 1 nanosecond, but the time precision is 100 picoseconds, means that I can actually talk about 0.1 and it would mean 100 picoseconds. It also means that if I write down, for example, 0.01, that cannot be represented within the time precision that I have. It would normally just get rounded down to 0. Maybe 0.09 might get rounded up to 0.1 or 100 picoseconds. That depends. That's something that you will have to look at the internal implementation of the simulator. The point is, 0.01 does not have a meaning in this time scale that we are talking about for the simulation. It will just get ignored. Okay. So what we can do is, we can, for example, within an initial block, we can basically have a hash 1, which basically tells us, once you have got to this point in the simulation, wait for 1 nanosecond before making any updates. After that, wait for 0.1 nanoseconds or 100 picoseconds before making any other updates. Now, timing diagrams are a very important and useful concept. We will be encountering them extensively as we move forward, right? And they are a very good way of sort of visualizing what happens with various different kinds of transitions that we have in system. And in this case, I am showing you a timing diagram which basically has, it's basically a module. As you can see, it's a test bench because it does not actually have inputs or outputs. What I do have over here is, there is logic in1, in2, out. Now, you might wonder, where is the DUT in all of this? And well, even though I said that test benches typically have a DUT, there is nothing fundamentally forcing you to have a DUT in there. You could think of this module, which is an assignment statement, as being a DUT, but I could also have something which doesn't have a DUT at all. It just basically has initial blocks out there and runs through as a piece of code. Okay. So keep that in mind, that even the idea of initialization, DUT, then the stimuli and so on is more good practice rather than something fundamentally forced on you by the language. In this case, I am trying to illustrate something. I am trying to show what a timing diagram would look like. So I have these signals declared over here. I have an assignment statement. I am just using the easy way of basically declaring what a signal would look like, right? And what I have over here is I have the statement which basically says #2 in1 equal to in2, or rather out is equal to in1 ampersand in2. Okay. And what I can do is I can say in1 equal to 0, in2 equal to 0, right. So you can see that at time 0 I have in1 and in2 both equal to 0. At 5, right, #5, that is to say I wait for 5 nanoseconds and then I make in1 equal to 1. Now the interesting thing is, after another 5 nanoseconds I am making in2 equal to 1. So you will see that in2 automatically became 1 only at 10 nanoseconds. It became, that is to say, 5 nanoseconds after the previous condition was, after the previous statement was executed. Then after another 5 nanoseconds I make in1 equal to 0. So there is this ordering that we see over here, right. This is 5 nanoseconds and then there is another 5 nanoseconds out here, right. So that is where these two are coming in. Okay. And well, if I monitor the changes, what I will find is that after both in1 and in2 have become equal to 1, out becomes equal to 1 because it is a ampersand, the AND functionality. Now there is actually a minor error in this diagram. This should not be at this point out here. Where should it be? If you think about it, this should actually have been at 12. Why is that? Because I am basically saying that after 2 nanoseconds I need to assign out equal to in1 and in2. Okay. So similarly this sort of falling over here would also happen after a certain amount of time, right. So that is used in order to model so-called propagation delay. We will be talking a lot more about that later. But the important point is you can see how the notion of time works, right. All this happens at time 0, then I wait for 5 time steps and make in1 equal to 1. I wait for another 5 time steps, that is relative to where I stopped last, which is why in2 becomes 1 at time 10. Another 5 nanoseconds and in1 becomes 0 at time 15. Another 5 nanoseconds, and actually speaking my simulation is going to stop out here, so I do not really have any of this after that. Okay. But well, in reality that's, if you actually had a circuit, this is what would have happened. The functionality would have continued changing after a certain amount of time and so on, right. So I don't in fact this falling over here is actually unrelated to this fact over here, because it should have fallen 2 nanoseconds after this itself. It should have fallen out here. Okay. So there is an error in this diagram, but it still shows you what exactly is the way that timing diagrams are generated. Okay. Now timing diagrams in general are a very good way to visualize different kinds of transitions, and they show, one thing that you will notice over here is this sort of a small delay between the time 5 and when in1 actually becomes equal to 1, right. So this change actually makes it explicit that this change in in1 is going to happen just after time 5. Why not exactly at time 5? Because in physical reality every gate has a certain capacitance associated with it, which means that voltages cannot abruptly instantaneously switch from 0 to VDD. They take a certain amount of time. And this is a common convention that we follow, which basically says that okay, if I say that something changed at time 5, I will show that it changed soon after time 5. Okay. There is really, this does not mean that this change happened at time 5.5 or at 6 or anything like that. It's basically used in order to show that it happened after time 5. If I actually wanted to show that this change happened at 5.1, I would need to change my timing diagram so that the notion of 5.1 is explicitly marked over here, and then I say okay, after 5.1 it changes, right. Like I said, this is a convention, right. you could also have a timing diagram where you just explicitly change at exactly time 0 or at time 5. There are certain simulators that will show you the picture that looking that way. Having it going slightly later like this is a common convention because it makes it explicit that there is a certain, the causality effect. This changed as a result of something that happened at time 5. Okay. Now, most of the timing diagrams that I am showing over here were generated using an open source tool called WaveDROM, right? And this is an online editor. You can basically type in JSON format and it will allow you to generate these kind of pictures, right? So, please play around with that and use that in order to generate timing diagrams for your own internal documentation. Now, timing diagrams are just one part of the visualization. What we need to do is to actually go in there and understand gate delays themselves, right? And this example that I have over here is essentially something that shows gates with different delays, right? What we have over here is we have effectively an AND gate but with a 2 input or a 2 unit delay. I then have something which basically takes the output of that temp, whatever was computed out here, and with a 3 unit delay it assigns a value y, okay. And I have a test bench that basically goes through and says, okay, initially start out with a equal to 0, b equal to 0. After 6 time units make a equal to 1, b equal to 1, okay. And then after that, we want to see when exactly does the output change, and as you will see from this timing diagram, I have a equal to 0, b equal to 0 out here. For the first 6 time units nothing has happened, they basically remain constant. After that, abruptly a and b both become equal to 1, and as you can see I have made them 1 corresponding to time 6, they reflect just after time 6. Now, look at this assignment statement. What it said was, if a and b changed, after 2 nanoseconds temp should change. And that is what we see in this diagram, right, 2 nanoseconds later, and that is why these arrows are showing that there is a causal dependency. The fact that a and b changed over here is what is causing an update in temp at this point, okay. Temp changes to 1 at this point, and once temp changes to 1, 3 nanoseconds later I should see that y changes to 0. So once again there is a causal relation between the temp changing and y changing, okay. This can be used to model the delays associated with individual gates. Now, delays of gates is something that you might not have paid much attention to so far, because when we talk about the basic introduction to digital systems, we assume that gates are some kind of mathematical abstraction, right? An AND gate simply takes its 2 inputs, waits, or and if both the inputs are 1, the output is going to be 1. If either one of the inputs is 0, the output is 0. We do not say anything about waiting for time or how long after the inputs change does the output change and so on, right? Because from a pure algebra point of view, there is no such notion of time. Physical reality, however, is different. An AND gate is actually constructed out of circuit elements like transistors, right, and wires, each of which has certain capacitance, resistance and so on associated with it, which means that voltages cannot rise and fall instantaneously. Net result is that there are usually delays associated with every kind of gate. AND gate in this case has been modeled with having a 2 nanosecond delay, right. So after 2 nanoseconds the output updates. The inverter, the NOT gate, has been modeled as having a 3 nanosecond delay, right. The important thing to keep in mind is you can use this in order to model certain gate delays if you want. However, keep in mind that Verilog is only a modeling language, right. The fact that I assign something with a #3 delay out here does not mean that my physical inverter that I use for building up my circuit actually has a delay of 3 nanoseconds. The delay of the inverter will be something else which is determined by how it is actually constructed. It may be much less than 3 nanoseconds, it may be more than 3 nanoseconds in certain cases. The important point is the number that you put in here by itself cannot influence what the delay of the physical inverter is going to be. This is something we use for our internal modeling. By putting in a delay over here, you cannot say that, oh, the actual physical circuit will also have a delay of 3 nanoseconds, right? That's an important aspect to keep in mind. It's a common source of confusion for a lot of people. They say, okay, but I put in a delay of 3 nanoseconds, so my inverter should have a delay of 3 nanoseconds. It does not work that way. The inverter has a delay which is based on how it was made, right? The delay that you put into the code over here cannot directly guarantee that you will get the same amount of delay in the inverter as well. Okay, so this, in other words, is a simple way of modeling basic kinds of delays. You could also have multi-path delays. What that means is I have multiple assignment statements over here, and what I am saying is, look at this y. It depends on P1 and on P2, and P1 and P2 individually are coming from multiple different sources, each with different delays. Okay, and if I run this through and see what the output looks like, it actually looks something like this. I have A, B and C as my top level inputs. In turn, they construct P1 and P2, and finally they construct Y. So what I see as a result is, this change in A causes an update in P1, which in turn causes an update in Y, right? So the delay from A to Y turned out to be a total of 3 nanoseconds. Okay. Now what happens when I change the value of C? I can find out from this that, C in turn is going to cause a change in P2, and that P2 in turn is going to cause another change in Y. But if I look at this, the difference between the change in C and the change in the output Y is 4 nanoseconds. So effectively what it's saying is, different inputs can have a different amount of delay by the time they reach the final output, because of the path through which they progress. A goes through P1 and then directly to Y, C goes through P2 and then to Y. P1 and P2 had different computational delays according to our model. In practice, they will actually have different computational delays, because this AND gate and this AND gate may be of different sizes, may be having different lengths of wires associated with them. The reasons why they have different delays could be many, right? All that Verilog says is it allows you to model it. But like I said, the fact that you have put in 2 nanoseconds or 3 nanoseconds does not guarantee that that's the actual delay in the physical circuit that you have. Okay. So some key points to keep in mind: simulation time is discrete. The time step that we provide, the time precision that we provide actually sort of helps us to put a limit on how fine the notion of time is that we need to go through. And it's important that, even though we might have the option of saying 0.1 nanoseconds, or you could say 1 picosecond, you could say 1 femtosecond, right? And what that means is, you actually want to sort of step time forward in multiples of 1 picosecond or 1 femtosecond. Having it too fine grained can be problematic. It actually slows your entire system down. If there is a specific reason to do so, then yes, you might very well need to put in a fine grained time precision. But in general, in most cases, delays in simulation are something that you need to be very careful about. Like I said, they do not always match or correspond to delays in the real hardware. So you have to be careful about what exactly you are trying to model when you go through with something like that. Now, as we go through multiple gates, as we saw, when we go from A to P1 and then P1 to Y, the delays accumulate. That's our internal model. Is that actually how things happen in practice? Well, generally yes. We have a signal that changes, that in turn causes some other thing to change, that in turn causes something else to change, right? So there's a cascading effect, and so therefore the delays can be considered as adding up. Multiple paths can of course have different delays. Timing diagrams are a very useful tool to visualize this kind of behavior, right? And monitor statements that we have already seen can also help to track such changes, but in a lot of cases it turns out that having timing diagrams is actually more useful and easier to understand than having too many monitor statements, because there's a lot of text that gets printed out and is hard to really interpret easily. As I said, use an appropriate timescale for your design. If you are, for example, trying to model a microcontroller running with a 32 kHz clock, then having a 1 nanosecond time scale is probably a bad idea, because it will slow your simulation down too much. But on the other hand, if you have, let's say, a processor that you are trying to operate and simulate where the internal delays are on the order of hundreds of picoseconds, right, maybe a 2 gigahertz or 3 gigahertz processor, then obviously you cannot set your time scale to be 1 millisecond, because you pretty much lose all the information corresponding to timing. Okay. So using the appropriate time scale is quite important for any form of design.